for those of you who are currently building or looking to building anything in the decentralized AI space, we are hosting this decentralized AI build-a-thon. And of course, Privacy, our speaker today, is one of our sponsors for the build-a-thon, which we're aiming to push forward the boundary of the crypto AI space and basically helping developers to build the project they would like to build with all sorts of infrastructure in the crypto AI space. And if you have any idea or wanted to build a project in the space, definitely joining our decentralized AI build-a-thon. And for today's workshop, we're hosting Rookie from Privasea, and he's gonna introduce a fully homographic encryption to those of you that are interested in this topic. And let's have Rookie to start his workshop.
Okay, thank you, Jen. Thank you for your introduction. And hello, everyone. Thank you all for joining today's workshop. I'm Rookie from Privasea, and today we are going to explore a cutting-edge topic at the intersection of cryptography and artificial intelligence. Our topic is fully homomorphic encryption and its application in face feature recognition. This presentation will not only cover the technical aspect of FHE, but also demonstrate how it can revolutionize privacy-preserving machine learning and biometric authentication. So can you all see my screen sharing? Okay, so then I will continue. To a roadmap of our journey today, we will go through the following topics. The first is the essence of privacy-preserving machine learning. And the second is the innovation fusion of FHE-based machine learning with the Privasea network. Then I will introduce some fundamentals of fully homomorphic encryption and give an overview of privacy face feature recognition. Finally, I will introduce our face recognition application. Okay, first let's begin with privacy-preserving machine learning. So why privacy matters? In our digital era, data now is often linked to the new oil, a resource of immense value propelling industries forward, from automotive to finance. However, with great values come great responsibility, particularly to protect individual privacy. The privacy-preserving machine learning, with a PPML, aims to extract value from data while ensuring that the sensitive information remains confidential. You can see this slide that the machine learning can be divided into a supervised learning, such as key nearest neighbor, linear regression, logistic regression, support vector machines, decision trees, random forest, and so on. And some unsupervised learning methods. Okay. Our PPML, privacy-preserving machine learning, marries this method with some privacy-enhancing technologies. You can see the right. There are some maybe some cryptographic techniques such as secure multi-party computations, including double circuit, obvious transform, secret sharing, and so on. So the MPC allows multiple parties to jointly compute a function over their inputs while keeping those inputs private. That is MPC. And differential privacy. Differential privacy adds some noise to data to prevent the identification of individual data points and output security. The federated learning maybe is more familiar to us. It enables model trainings across multiple decentralized devices without sharing rough data. And maybe there is also a hardware solution. It's called Trusted Execution Environment. We say TE. It provides secure areas within a processor to execute code or data securely. Maybe like Intel SGX, like this. Finally, there is a primitive called homomorphic encryption, which is the key technique in privacy and also in this presentation. So we will give a detailed introduction later. Okay. Okay. Then we come back to PPML. We can see privacy preserving machine learning system like this. At the heart of this system is the protection of sensitive data. You say sensitive data. Representing here by X-ray, a type of sensitive health information that requires protection like this. The client means individuals or entities with private data, such as medical records that hold the key to potentially life-saving insights. The server presents the secure and private prediction platform, which in this case is focused on medical prediction without exploring the underlying personal data. So it should use the privacy-preserving machine learning to train or predict without ever access the raw data. You see the X-ray or the result is encrypted. Use fully homomorphic encryption or some other private enhancing technologies. So it can ensuring that personal information remains encrypted and secure through the process. This is we say privacy preserving machine learning. Okay. Okay. Then we will introduce the FHE-based machine learning and our C network. FHE-based machine learning leverage FHE, fully homomorphic encryption, to enable AI processing. This is a demo. You can see this is a demo for handwritten digit recognition. We use FHE. You say this encryption scheme is FHE encryption. So we use FHE to encrypt the image and upload it to the server. Then the server can recognize accurate numbers from the ciphertext. And then it gives back the ciphertext result to the client. Then you can see that this is an image, and then this is a result presented by an integer. Okay, so you can obtain this demo from our official website, Privasea Web. So FHE ML offers several benefits. The first one is that it can ensure data value circulation for AI while maintaining data ownership. Like this example, the image will not export to server. The server only can see the encrypted method. The encrypted message, like TLWE message, is a kind of encryption method. Yeah, and it can provide privacy components. So this is FHE ML. However, the FHE ML, the computational load of FHE is significantly. So maybe it can cause some computational pressure on closed servers. If we use just one closed server to deal with such a big amount of data and a big amount of calculation, so maybe it's not a good idea. So what if we leverage the power of blockchain distributed computing power? This is our Privasea AI network. It is a distributed privacy-enhancing computational network that allows users to control their data without the risk of leakage during AI processing. Especially, we have utilized the machine learning technique to mine the value of data. And we use the privacy-enhancing technology, especially fully homomorphic encryption, to protect user and data privacy. And finally, we use the decentralized distributed computing power on blockchain to provide computing power support for the network. This is our Privasea AI network. Yeah. So the above is the overall introduction of our Privasea FHE ML. Next, let's go into some technical details, especially the fully homomorphic encryption. So now, do you have some question about our architecture, or? Okay, of course. Then I will go through the fully homomorphic encryption. First of all, what is encryption? You know, encryption is the process of converting information or data into a code, like privacy into this code, particularly to prevent on the access. It involves transforming the readable data known as a plaintext. We say the plaintext or messages of a C. We transfer this plaintext into an unreadable format called ciphertext, like this. So only those who have the secret key can convert the ciphertext back to plaintext and access the original information. For example, this is the AES encryption. So we use the AES standard encryption to encrypt Privasea to such a ciphertext like this. Okay. So encryption involves confusion. This ensures that the data cannot be understood without a key. You can see nothing. But fully homomorphic encryption is a special kind of encryption algorithms that it allows computations to be performed on encrypted data. We have a GDPR or DARPA have a DP right. Maybe this tool. This tool is to it requires us to protect the user's data or the identity. So we need the privacy enhancing technologies. The fully homomorphic encryption allows computations to be performed on encrypted data without need to decrypt it first. We give an example here. You see that, for example, the encrypted X plus the encrypted Y equals to encrypted X plus Y. This means the sensitive data can be processed while maintaining its confidentiality, like this. So our privacy use this fully homomorphic encryption, and Zama and some other project also use fully homomorphic encryption. It's a mainstream privacy enhancing technology. The evolution of fully homomorphic encryption has been remarkable. is starting from a partially homomorphic encryption, like PHE, which only support a single type of operations, to somewhat homomorphic encryption, SHE. It can support a certain number of additions and multiplications. And finally, the fully homomorphic encryption, capable of performing an unlimited number of arbitrary operations on encrypted data. The length space of FHE is dotted with several mainstream schemes. For example, such as BGV or BFV schemes. These two are good at arithmetic circuit computations over finite field. And CKKS scheme. This scheme supports approximate arithmetic circuit computations over real or complex numbers. These two tabs, BGV, BFV, and CKKS, are collectively referred to wordwise scheme, like this, wordwise, because a ciphertext it can encrypt a word instead of just one bit. So we say the wordwise FHE. And there are also few and TFHE schemes. These two schemes are good at Boolean circuit computations, so it referred to bitwise FHE. These mainstream algorithms are designed based on LWE or RLW problem. Then we will go through some technical details. This is LWE and RLWE hard problem. The learning with error, LWE, is a fundamental hardness exception for many cryptographic systems, including FHE. It involves distinguish between these two distributions. The first is a set of linear equations with some small noise like this. And the second is a set of random equations. So in mathematical terms, given a dimension n, a modulus q, and an error distribution over the integers, e. The LWE problem requires distinguish the distribution A, S plus E, and a uniform random distribution, where A is a random matrix and S is a sequence. The ring learning with arrow problem is an extension of the LWE problem to polynomial rings. It involves distinguish between a set of ring equations with some small arrow ei, maybe e1 to en, and a set of random ring elements. These two problems are hard, so we can use them to encrypt a message. For example, if we want to encrypt message M, then we can use AIBI plus M. So, LWE and RLWE ciphertext like AB plus M, it naturally has additive homomorphisms. So the core problem is that how to construct the homomorphism for multiplication. The wordwise schemes use scalar product. The scalar product like this, maybe C10, C11, scalar product C20, C21. The result is like this. Okay. The key problem is that the ciphertexts are all vectors, like this, this one and this one. So thus it cannot, which cannot maintain their original form after scalar product. For example, these ciphertexts have 2 dimensions. This ciphertext has 2 dimensions, but the result ciphertext have 4 dimensions. So, so the wordwise schemes propose key switching techniques, like this key switch, key switching techniques and modular switch to change back to the original ciphertext size to support continued multiplications. You can see that the key switch techniques transform the 4-dimension ciphertext to the original 2-dimension ciphertext. Then the word-wise scheme can do more multiplications. Okay. And the bitwise schemes uses external product such as this formula. We omit to introduce the details here, but it need unlike the word-wise schemes, it need some auxiliary input like the RGSW ciphertext, but we omit some technical details here. These constructions, these two constructions leaves us somewhat homomorphic schemes. I remember somewhat homomorphic encryption schemes. Somewhat homomorphic encryption schemes, it is possible to perform a finite number of homomorphic operations. So the common problem is that how to construct fully homomorphisms to realize arbitrary operations. Then we use bootstrapping technique to solve this problem. It can refresh noise. For example, it can refresh E from the LWE or RLW ciphertext. Okay. The bootstrapping procedure, it is a key procedure. Also, the performance bottleneck of the homomorphic encryption. You know, the bootstrapping time of a word-wise scheme often reaches tens of seconds or even a few minutes. The bitwise scheme bootstrapping faster, but other calculations are slower. So, the word-wise fully homomorphic encryption schemes and the bitwise schemes, they support different kind of operations. Here are some typical FHE-based machine learning schemes, especially Cryptonize, Lola, and Paxos. Cryptonize, CryptoDL, faster Cryptonize use the set generation for example, we say the second generation is word-wise FHE, and these three methods use the third generation. For example, DINN is a bitwise FHE. Okay. And there is also a switching method, camera or Paxos. It switch between word-wise FHE and bitwise FHE to support different kind of operations. Okay, so this leads us challenges in FHE ML. The challenge of FHE ML comes from the complex operations in neural networks. For example, a neural network to clarify cat or dog or frog is like this. It contains linear operations like the convolution layers or fully connected layers or like average pooling layers and so on. But it also contains some non-linear operations. For example, the activation functions such as ReLU or the max pooling layers. So the convolution layers is like this. It can use a linear formula to cover this layer. Okay, so the CNN computation unit is very difficult and complex to FHE. So the machine learning models are always large, and the functions are complex and FHE unfriendly. So these two are the main challenges in FHE ML. Okay. We give some more examples. For example, if we use word-wise schemes, you can see that the word-wise schemes are good at some linear functions. For example, the plus or multiplication or some polynomials. It is very fast if we use the word-wise schemes. However, when we want to use the bitwise schemes, because it can only support the Boolean circuits, then the multiplication or the addition is very slow. However, the bootstrapping is very fast, and if we want to do some nonlinear functions like ReLU, like lookup table, the bitwise schemes are good at this. So the main challenge is that the functions are very complex and different method or different fully homomorphic schemes support different kind of operations. So we say ML, machine learning, PPML or neural network is FHE unfriendly. Okay. So let's take a look at how Privasea solve these two problems. And I will introduce the Privasea face feature recognition. Okay. Privacy's face feature recognition system uses fully homomorphic encryption to perform a secure biometric authentication. This system can check can check the similarity. Is a person holding the ID is the same person showing the ID photo? So ensuring also it can ensuring both similarities and liveness. It can check if whether the person holding the ID physically present during the transaction. This is our vision, the Privasea face feature recognition. Okay. The workflow is as follows. We use ResNight 18 to extract the encrypted embedding vector, and we use FHE to realize face recognition homomorphically. You know, if we just extract the feature vector, but without using FHE, then your photo or your feature vector will expose to the server. Then the server maybe use this to do something bad. Okay. But to enhance the recognition the performance, we should do some to solve this the two key problems we have already talked about. So the Privasea systems employs two key solutions. Firstly, we divide the recognition model. So first, let's consider that a few questions. First is what data is really sensitive. You can, if you have some idea, you can give me some answer. What data is really sensitive in a face recognition system? Your face picture or embedding vector? What do you think about this question? Okay, no problem. So, what data is really sensitive? It depends on for the client, which one will out of control. So if we track the embedding vector, and then we if we just extract the vector to the server, then the vector is the key sensitive data for us. So we divided the recognition model and this picture and this part. The first part, we use ResNet 18 or ResNet 34 to extract the embedding vector. But the feature extraction part was completed locally on the clean set. So it is very fast because it is completed locally and in the plaintext state. Then the extracted feature vectors results will be encrypted and transmitted to the server. So this is our encrypted part using fully homomorphic encryption. Then the server performs homomorphic compression operations. This can make our system simpler and faster because we divided the model to a plaintext space and a ciphertext space. Okay. So we solved the first problem, and the second core solution is a secure face match. The comparison operation was achieved by the oscillating distance, like this, x squared plus y squared is oscillating distance. However, this function is a homomorphic unfriendly function. So we retrained our recognized model using a cosine distance. Like this, the cosine distance is also not friendly for the homomorphic encryption, but we can use such a inner product like this. We use one manner sigma xi yi. Just the inner product consists of multiplications and additions to implement the secure face match. So then the result is that we can achieve the homomorphic facial recognition in seconds. Okay. Okay. Our Privasea FHE-based face recognitions can be applied in various scenarios, such as secure KYC procedures for decentralized applications, or anti-symbol authentications, or liveness check for biometric authentication, and so on. Okay. And this is our application. This is our I'm Human application. It can verify your face liveness, and you can get this demo. You can get this application in our official website. Okay. So okay, then yeah, we have some extra time, so I will introduce more about the FHE and FHEML. Okay, fully homomorphic encryption, it can represent a significant advancement in the field of privacy preserving technologies, because we say like this formula, by enable computations on encrypted data, we can FHE ensures that the sensitive information remains secure even during processing. Sorry, I will back to this slide. This is FHE-ML gives us the FHE-ML consists of such 4 steps. The first one, the client maybe have some sensitive data like medical data, financial data, or even government data. So it can encrypt the input to the cloud or just the server. Then the server do the homomorphic evaluation without decryption. So the cloud cannot access to your rough data, or it can't explore your data to any untrusted third parties. Okay, so it do the homomorphic evaluation and then give back the encrypted response. Then the client decrypt the response. So our privacy feature, face feature recognition is also like these 4 steps. First, in the client, we extract the feature vector, and then we encrypted our feature vector to the cloud, to the server, and our server consists of many computation nodes because we use blockchain decentralized computation powers. And then our cloud homomorphically evaluate the cosine distance to make sure that your picture is your picture is consist. And then the server will give back an encrypted response, and the client decrypt the response and find the result. But however, this is also a question that how can we share the result with a third party? Our privacy AI network also have a decryption or decryptors. The decryptors can do a proxy re-encryption, or we say a key MS, key managed system. The result decrypted by the decryptors can be shared to the any third party, but it's also secure and privacy because we use a proxy re-encryption method. It means that for example, if Alice wants to share the result to Bob, then the message, the data, the Alice encrypted data will be transferred to the Bob encrypted data by the decryptor and our proxy re-encryption method. Then Bob can decrypt its own ciphertext. However, Bob cannot decrypt the Alice ciphertext. So this procedure is also private and secure. This is our whole privacy AI network. Okay. So in conclusion, fully homomorphic encryption gives us advance in privacy preserving machine learning. So we computations on encrypted data, so we can ensure that the sensitive information remains secure even during processing. So the application of FHE in machine learning and biometric authentication is demonstrated by our privacy network and our face feature recognition system, shows the potential to revolutionize data privacy and security. You can access our website to download our white paper or download our application and try it by yourself. It's very interesting. And now our application is our Android application. You can get it from our website, but for Apple, maybe you should wait several days. We will give the application maybe in this month. Okay. The application is like this. First, you should set up when you create an account you should upload a picture, your own picture, and you should do the liveness check. And then if you already have an account, if you want to check if you want to do the verification, you should give another picture, and then our privacy network will compare these two pictures, but without using your raw data. We use just the encrypted data. So then you can test your liveness and verify human, and then the liveness check maybe will pass. And if you have a just created account, you will have your own NFTs and your own reverse. So you can try it by yourself. Okay. This is our official website. And thank you for your attention. I hope you found this presentation insightful and informative. Okay. I would now like to open the floor for any questions you may have. Thank you. Thank you, Law. So, do you have some questions? Yeah, feel free to type your questions here. Yeah. Maybe for PHP or for our privacy network or for privacy preserving machine learning and so on. Feel free to talk with me. Okay.
Okay, I've actually seen someone raise my hand. Sorry, I didn't pay attention to that before, but I'll invite you to speak now.
Pardon, sorry, I see a question. What
Yes,
is
someone
the
was
advantage
there.
of, yeah?
Sorry,
what
I was
is the
just gonna say
advantage-
someone was raising their hand, and I invited.
Oh,
to
okay,
speak.
okay. Okay, I see a question is that what is the advantage of FHE over ZK? Yeah, ZK is ZK is a zero knowledge proof system. It's just the functionality is to prove and verify. One can prove maybe I have the answer of this question and I can prove I have this answer for you. But there are nothing other functionalities. However, the fully homomorphic encryption has it's more powerful than zero knowledge proof, because we can do any calculations, uh, any any types of calculations. For example, the machine learning. Yeah. Not video count out. Uh, Adrian can help me for these two questions. They say that maybe have internet issue. They can't log.
It's weird because I can see the screen sharing on my side.
Okay.
So it's probably just their network issue. But let's keep the floor open for 3 more minutes. If anyone has any questions, feel free to raise your hand or type the question directly on the chat box.
Okay, so do you have some other questions? Adrian, maybe this question is for you. What are the prizes in part of track prizes?
Yeah, so for the build-a-thon, we have several tracks um, of the bounties, which are offered by different partners, including like DK Pass and Near. So I think the one that was you're saying like I like to build Web3 social DMs using Gen AI also. So if it's something related to agent, you can definitely apply for the Near bounty. And for the general tracks, what we're gonna do is we're gonna do a community voting for all the projects that have been submitted to the build-a-thon. And the top 10 project will be rewarded by like prizes. And I actually see another question asking, what are other use cases can FHE be used other than KYC?
Okay. So, FHE is very powerful. Other than KYC, it also have lots of applications. First, the privacy preserving machine learning can do some. It enables secure computations, make it ideal for privacy preserving machine learning models. Any models, not only the face visual recognition. So it can use for secure model training, prediction, and inference while preserving data privacy. And it can also do some secure cloud computing or secure delegate computing, because it allows users. FHE allows users to allows servers to perform computations without access the raw data. So the cloud computing or the delegate computing can be safe, and it will not leakage user the client's raw data. Okay, and it can also do some private data sharing and collaboration, and some financial service use and some financial service and some medical service. And we also do secure voting systems, because it's very simple because if I want to if I want to vote to some person, we can give a 1 instead of 0, and then we add this result using fully homomorphic encryption, and then we have a secure voting system, something like this. Okay. As another question, it is possible to achieve private data feed to private model through FHE. Okay, it's a good question. Um, we now talking about it is maybe just a two-party FHE, a client and a server, and the client have some sensitive data, but the server do not have a sensitive model. However, your scenario is another scenario that maybe the data and the model are also are both sensitive. So this we should use a multi-party fully homomorphic encryption, or we say multi-key fully homomorphic encryption to deal with such scenarios. It means that the client can use his own key to encrypt his private data, and the server can also encrypt his model by his own key, and we do multi-key FHE. But multi-key FHE now is much slower than our original FHE. Yeah. Multi-party. Maybe I will. Multi-party or multi-key FHE. It's interesting that Dama has another solution for this scenario. They use a global key. They also have a lot of parties, but they all use the same key pairs generated by an MPC protocol. I think it's also an interesting solution. Yeah, of course. If you want to, you can contact us through our Privacy AI website.
Awesome. Yeah, so I think that should be all for our workshop today. And because this session is recorded and will be put it on our website for all the participants of the Buildathon to view. And if I get any further question, I'll just forward to the privacy team. And if you want to contact with the privacy team directly, feel free to DM me or any of our Aspecta team member. We'll create a group chat for you. Okay. Then thank you, Rookie, for your workshop today. And
Okay, thank you.
So, hope it. Bye, everyone.